What's going on, everybody? Mr. Diamond here with your what I hope to be the final advanced chemistry notes that you guys have. Now, for seniors, that's because you guys are going to be graduating, obviously. But for everybody else, you guys already have that book project that we're going to be working on. So I just figure we're going to have a nice kind of smooth into the year. This is the last section of notes, and I kind of mentioned it, I believe, in the daily log for yesterday. But there is no math in this section. You don't really have to do any. There's like in your head calculations, and I mean literally like adding like 4 plus 2 or math like that. There's some pretty straightforward ones. But there is no calculations. There's no possibility of a quadratic formula. There's no anything like that. So this is section 5, stress and Le Chatelier's principle. Le Chatelier is how you pronounce this. Now, some of you might be thinking, man, like a whole section dedicated to stress in chemistry? Is the class becoming like self-aware or something? Well, obviously not. The class would never become self-aware. When we talk about stress in regards to chemistry, usually we're talking about stressing a system or a reaction. And you might also be thinking, okay, well, what do they have to stress about? Like, do they have exams? Does hydrochloric acid have some sort of like secret love life that we aren't aware of? And again, not exactly, though I think that there was a band about some sort of like relationships between like chemicals. I don't know. I'm probably off a little bit though. So in this case, when we're talking about stress, we're more talking about like disturbing the system in some way. Changing the conditions puts stress on a system that was already equilibrium, so it will respond in some way. You might have thought that you were kind of feeling really good about the year, and you kind of had an idea about how everything was going to go, how everything was going to work, and you didn't really need to worry about too much. And then COVID-19 comes along, and here we are, me sitting in my pajamas recording a video to send you about, chemistry. And obviously, we are no longer at that balanced point, at that equilibrium point that we thought we were going to be at. And so we respond in some way. Some people respond by baking a lot of stuff, which I've done. I've baked a lot of bread. Some people respond by gaining a lot of weight. Some people respond by working out for many hours a day. But we do something to respond to that stress. Conveniently, reactions are a lot like people. Whenever you get stressed or reaction gets stressed, both will try to avoid dealing with it as much as possible. And usually they just want to go back to how they were before the stress. This is probably going to be one of the more relatable sections of notes you'll take. Now, this idea of avoiding stress was laid out in one of the most fundamental and foundational principles of modern chemistry, Le Chatelier's principle. Pronounced not, it's not Le Chatelier, like it is Le Chatelier. I believe he is French, as you could probably guess based on that name. But Le Chatelier's principle states that if a system in equilibrium is subjected to a stress, the equilibrium will be displaced in such a direction so as to relieve the stress. Notice it says in a direction. This is because we actually describe it as shifting to the left or shifting to the right. Most of your answers for this section will be either an arrow to the left or right, or since you're typing them, it'll just be you typing the word to the right or to the left. So as usual, the easiest way to kind of talk about this reaction is to look at an example. So we're going to be sticking with this one right here. We have PCl5, that's phosphorus pentachloride. It's in gaseous state, and it reversibly reacts to form phosphorus trichloride, that is a gas, plus chlorine gas, which is Cl2. Now there are 4, I'm holding up my hands, but you can't see it, 4, I guess my fingers, not my hands, but 4 fingers. So there are 4 different ways that we are going to look at equilibrium shifting: concentration, pressure, volume, and temperature changes. So first, let's assume that while the above reaction is equilibrium, we add more chlorine gas. What is going to happen? And then we're going to also ask, what about if we removed some phosphorus trichloride from the container? What would happen then? So I want you to go ahead and try to, in your head, remember the answers are to the left and to the right. If you added more, or to the left or to the right, if you added more chlorine gas, do you think that's going to make it shift to the left, or do you think it's going to make it shift to the right? And then the same thing for if you add or remove PCl3. If you remove some of this, will it shift to the left or will it shift to the right? So if we add more chlorine gas, that means that there are more reactants than there were previously. There is more on this side of the reaction. And because equilibrium is affected, it's going to try to rebalance. If you remember, equilibriums have a specific value, KEQ or KC or KA or KSP or whichever one you're using. In this case, I'll continue using KEQ because it's the general one. Your KEQ requires there to be a specific ratio between products and reactants, and you just disrupted that specific ratio that they had already achieved by adding in more reactants. Because there are now more reactants on this side, to get back to that ratio, it's going to need to turn some of that extra stuff you just added into reactants. This products that you've added over here, it needs to go back and become more reactants. I think I might have worded that backwards in my head, and there's no such thing as editing, so I can't check. So you've added more products, and that means that it's going to need to make more reactants to get back to that magical KEQ, that magical ratio that it had, that thing that all of the equilibriums want to go to. It's not actually magic, it's science, but whatever. So in this case, because we've added something more on the right side here, it's going to shift left. So the first rule that you can remember is that adding something to one side will make it shift away. So I usually, whenever I teach this, I can draw like a little arrow down here. I'll do like an up arrow, and I'll remember up and away. So Cl2 goes up, and so it's going to move away from that Cl2. Now, removing PCl3 is going to do the opposite. We've still thrown the ratio is off, but it's because we lowered the amount of products that was there. So we need to somehow get more products to rebalance what we have at equilibrium. And the way we're going to have to get more products is if we make or we use up more reactants. So if we use more reactants, it's going to end up making more of our products is going to move to the right side, and because it's going to then make more of the products over here and use up more of those reactants on the left side, we call that a shift to the right, because we're going to be making more of this stuff. So again, this one was up and away. This one is going to be, I don't have anything nearly as clever as that, so I usually just say down is towards. If something goes down on one of the sides, Le Chatelier's principle will cause it to shift towards that side. So reducing PCl3, we're going to move back towards PCl3, which is going to be to the right. Okay, pressure and volume both only actually care about gas particles, and that's because solids and liquids usually don't really react to those kinds of changes. If you guys haven't seen them, well, I apologize because I guess those of you who are seniors will never see them. But there is a gas chamber that I believe Zuspin has where we can actually demonstrate that, like, if you put an aluminum can in there that's open, the aluminum can's not going to do anything. It's just going to kind of change the amount of air particles that are kind of hitting around on it. But if you put something like a bag of chips in it and you remove the gas that's inside of that vacuum chamber, it will cause the thing to expand because the gases inside of that potato chip bag tricking you to thinking that it's fuller than it is when you buy it, so you don't realize how poor of a deal you're actually getting, is a gas, and those gases are affected by pressure and by volume. The other reason so that's for pressure there. The reason it works for volume is because solids and liquids do not fill their containers. They just kind of sit in whatever container it is. When you pour like water into a cup, which is my reminder, stay hydrated. I'm going to get a drink real quick. But when you pour water into the cup, the water does not spread out to fill up the cup. Although if it did, it would be way cooler, and it would also be, way better for the world. But, we can't all get what we want. So when you increase pressure, what's going to happen is that there is more gas particles being forced closer together. And because of that, in order to fix it, we can't just say, well, we're going to make more, we're going to make less. If there's things being pushed together, the thing it will do is it will try to find the side that will make it less cramped. And the side that will make it less cramped or taking up less space in total is going to be the side that has less gas particles. Because if you look up here, this left side has one gas particle and this right side has two gas particles. So if we stay on the right side, even if as we increase pressure, there's now two of these things bouncing around. There's a Cl2 and there's a PCl3 that are just bouncing and bouncing and bouncing around. And at the PCl5, they're still going to be bouncing around, but there's only one of them. There's not two distinct gas particles. So the more of these products that we can shift back to the reactant side, the better the reaction will be feeling, because it's not going to be nearly as cramped. The space is not going to be nearly as difficult to deal with the amount of stuff bouncing around in there. I know this metaphor doesn't work perfectly, but I hope the concept is at least coming across here. So if you increase pressure, you go to the side with... hold on, sorry. I spaced out for a second. Had to pause the video. When you increase pressure, that means that there is going to be more gas particles, so you go to the side that has less gas particles. So in this case, the side that has less gas particles is the left side, so increasing pressure will cause it to shift to the left. It only has one gas. Now, if you decrease the pressure, that means it can kind of stretch out more. It can take up a little bit more space, so it will actually go to the side that has the most gas particles. In this case, because there's more space, the easiest way to fill it is by breaking these things down into two distinct particles and having them fill in that space and kind of expand a little bit. So lower pressure goes to the side with more gas particles. Now, I'm going to stop here. I think I have it on one of my slides, but just in case, when you count coefficients... as I accidentally hit the scroll wheel. When you count coefficients, this PCl5 is one gas because it is a gas and there is an invisible number 1 here. This PCl3 is one gas because there's an invisible 1 here and it is a gas. The Cl2 is a gas and there's an invisible 1 here, so that's one gas particle. 1 plus 1 is 2 gas particles. If there would be a number, if there would be a coefficient out here, if there's a number out front, you include that as the number of gas particles. So if this would have been like 2 and then 2 and 2, which, I mean, you would have reduced that to ones. But if this would have been 2, 2, and 2, that would be 2 gas particles and 4 gas particles. So coefficients do count when you do these problems for pressure and for volume. Volume works the exact same principle, but it goes the opposite direction. Increasing volume means there's more space, and more space, as we said earlier, means it's going to want to spread out to fill that space, and to spread out, it's going to go to the side with more gas particles. So in this case, increasing volume would shift to the right, and decreasing volume means there is less space, so the side with the less gas particles is favored, so we're going to shift back to the left. It's a kind of weird concept, but I hope that makes sense. I just explained so much more in pressure and volume are kind of related to each other. So the fact that I explained pressure so much makes me feel like I can kind of slack off a little on the volume part. Okay, for temperature, it involves a little bit more thinking, and I'm sure that the more focused ones of you have noticed that this little thing over here has been here, and we haven't used it. This delta H, this enthalpy change, if you remember this, we used this when we talked about heat of solutions, which was quite a bit back. That was last chapter. It probably feels like a whole decade ago for you guys. The main focus here is you want to remember from last chapter that this is the energy that is gained or released by a reaction. Positive of this number means that it is endothermic, or it requires energy to react. And that means if it needs energy to react, we could almost think of energy as being over here on the left side of the reaction. Negative delta H means that the reaction is exothermic, or that it releases energy when it's completed, which means we could kind of think of it as a product. So we could rewrite, with our knowledge of this, our equation into one of these, depending on how specific your professor is. Sometimes they'll write it either of these ways. Some will keep them separate, and I'm going to keep them separate because I want to make you think. But sometimes they will put like plus delta H or plus energy. Sometimes they'll put plus the actual number in there. But this, because it is positive, meaning that it is an endothermic reaction, means that it's going to be on the left side of the reaction. And from there, we can then actually start thinking about temperature. Now we're going to use this one, the delta H, because it's simpler and we don't actually need what the number is. So since that represents energy, and temperature, if you remember, is a measure of kinetic energy, we can just treat temperature the same way as we did concentration. If you increase temperature, well, none of these numbers or these substances involve temperature, but this one right here is a measure of energy. So increasing temperature means you're increasing energy. So you put an up arrow there, and just like before, up and away. We increased our temperature, so we're going to move away from that delta H, so we're going to shift to the right. It's going to try to get rid of that extra energy by making more products. And if we decrease the temperature, if we were to make it colder, we would drop this, we go down and towards. Decreasing it will mean this thing will want to warm back up to get back, because remember, KSPs and KEQs and all of those are at specific temperatures. So to get back to that proper ratio, it's going to want to, if you've decreased the temperature, it's going to go back to the reactant side, because if it goes backwards, it will make more energy, and that will heat the system back up and try to get it back to that equilibrium point. So temperature, once you know which side it's on, functions the exact same way as concentration. You just have to actually figure out which side it's going to be on. Okay, so with that information, here is my example problem for you. We have Ni that is a solid, so solid nickel plus 4CO, carbon monoxide gas, reversibly reacts to form nickel. It's carbon monoxide and 4 COs. I don't even actually know what the proper scientific name for this thing is, so don't worry, I wouldn't expect you to name it. Okay. And then we've got our delta H is negative 25.63 kilojoules per mole. Here are the 5 questions that I have for you. You don't actually have to write anything down, because again, there's no math, there's no calculation, but I would pause the video and try to think, are these pieces or are these things going to shift them to the left or to the right? And I will tell you for a heads up, because some of you will not think it's possible unless I tell it to you. You do have the option of neither. Neither is a reaction that is, or a thing that is possible to occur. So just keep that in mind. Not that there is one on here that is, but just keep that in mind for the future. So go ahead and pause the video and try to figure it out. I'll give you a few moments as I twirl my pointer and get a drink of water. All right, proper hydration is key. So we're going to add more carbon dioxide. Now, I did not actually intend for this, but I originally meant to write carbon monoxide, but instead of fixing it, I left carbon dioxide here, because carbon dioxide is not in the reaction. Now, it's similar to carbon monoxide, but we don't know that adding carbon dioxide is going to affect any part of this reaction. Maybe it'll react with nickel, maybe it'll react with carbon monoxide, maybe it won't do anything. So because we don't have more information, our answer for if you add more carbon dioxide would be neither. It will not shift either direction. It's not the thing in any of the problem. Now, sometimes if something is not in the problem, that does not always guarantee that it's just a no shift. We'll talk about that in a little bit. Okay, increasing pressure. So increasing pressure means that there is less space for something to exist in. Less space will favor the side that has the least amount of gas molecules. So nickel is a solid. We don't have to count that. Carbon monoxide is a gas, so there are 4 of them. Remember, this digit out front we do count. This is not one gas. This is 4 gas molecules that will be present. And then our nickel carbon monoxide compound thing here, we also have 1 of those that is a gas. So our left side has 4 gases. Our right side has 1. Pressure favors if you increase it, will favor the side that has the least gas particles. So that will shift to the right, because this side has only 1 gas molecule. Decreasing volume. Decreasing volume will do the same thing as increasing pressure. They are opposites of each other. So once you've solved one, you can actually just flip it and you've got the other one. In this case, increasing pressure would be doing the same thing as decreasing volume. That's less space, so the thing that's favored is the thing with the least amount of gas molecules. The thing with the least amount of gas molecules is the right side. So this one will also shift to the right. So here we so far have no shift, right, and right. And then what if we lower the temperature? Well, we have our delta H. It is negative 25.63. Negative means that it's going to be on the right side because it is an exothermic reaction. So we could actually think of NiCO4 gas plus negative 25.6 or 25.63. You wouldn't actually put the negative in there because the negative is just telling you which side of the reaction it's on. So if it's on this side and we lower the temperature, if we go down with the temperature, that means it's going to have to shift to the right because it's going to go down means it's going to go towards that side. So it's going to move this direction in order to try to generate the heat back again if we lower the temperature, and that means it's going to shift to the right. So now we have no shift. We have shift to the right, shift to the right, and shift to the right. Okay, finally, for number 4, we're going to add nickel phosphate powder. Now, like this one up here, you might think, well, that doesn't have anything to do with any of these problems. However, nickel phosphate powder is going to most likely have some sort of stuff breaking down whenever it is present. This is especially for when you're dealing with aqueous reactions. I couldn't think of a good one for this one, so I apologize. Like I mentioned a second ago, this was actually supposed to be carbon monoxide, and it would have shifted to the right. But we're not worried about that one. In this case, nickel phosphate powder will probably split into nickel and phosphate, and nickel is in the reaction. So one thing you want to look out for is if you add something that doesn't seem to be in the reaction, but a component of it is in the reaction, you could treat it like you're adding more of that. So nickel phosphate might not be there, but adding nickel phosphate will probably add more nickel. And if we add more nickel, that means it's going to shift to the right. I'm really bad, or I've noticed I've gotten really bad about mixing these up. So unfortunately, this is no shift right. And I honestly haven't. I think the worksheet is probably like that too. So don't freak out if you feel like your answers are all going one direction. I apologize. Yawning, tail end of a long day, but that is how Le Chatelier's principle works. As you can see by the fact that there is not a button for here for me to push, although it's kind of behind the dragon. We are done. This is the last section of notes. So this is going up on Thursday the 7th, I think. Dates are hard. Time has no meaning at this point. But on the 8th, which is Friday, I'll be posting some Le Chatelier's problems. Like I said, I know it's a little bit quick here at the very end with just like one day of practice, but this is really, and either you get it or you don't. I struggled with it a lot in high school because I kind of just assumed I got it, and then I didn't, and I've had to go back and learn it, and after learning it, I feel like it makes a lot more sense, but it's definitely tough if you feel like you get it and you just kind of pretend. But the concept itself is not super difficult. So tomorrow I'll have some questions about Le Chatelier's principle. Your answers will literally just be right or left. And then on Monday, Tuesday, Wednesday, will be the days available for your test. I'll post them on Monday. I don't have any review questions or anything like that for this chapter. If you have any of them though, can definitely work them out on Friday. If you have anything you want me to explain, or send me an email over the weekend, or honestly, you can send me an email during the test. I can't promise I'll help you with a test question, but I can help you kind of go through what your thought process should be, or work out any of the previous examples if you're stuck on those and you want some assistance with that. So I hope that makes sense. I hope you guys are having a great week. I know I usually say leave a comment in the box or an email, but really, I do not look at the boxes sometimes for a whole week, because grading is the hardest part about this whole situation, because I've just been making all this material. So if you have anything that you ever get stuck on or you can't get the right answer, please send me an email of it. You can send me a picture of your work. Or just send me hey, I keep getting this answer, I don't know what's going on, and or here's what my thought process was, and we can try to figure it out. But the boxes, if you type in them, it's nice whenever it's a day-to-day thought or a thought that goes along with the log, but if it's asking for help, I might not see it for a week. So please make sure that you actually send me an email about that. But I still do hope you have a good week. I hope you have a good rest of your day, and I hope to see/hear from you soon.